Welcome to We Design Plastics, a channel all about designing injection moulded parts. Hi, I'm John Schmidley, the owner and senior designer at Melbourne-based design house SCAD Design here in Australia. We Design Plastics is a YouTube channel where we share our knowledge in the best practice in designing plastic parts for the manufacturing process of injection moulding. In this video, I will take a typical injection moulded part and run it through our usual final check for release phase. Before we get stuck into today's video, I just want to let you know that we have a free downloadable PDF of our Release for Tooling Readiness Checklist. This checklist is what we use here at SCAD Design to ensure that every part we release for tooling is injection moulding ready. Just click the link in the video or go to scaddesign.com.au/WeDesignPlastics. So let's get into today's video. Okay. This part here, it's a part that's going to be moulded in acetal. It has a leaf spring arrangement there, a shaft that it rotates on, a finger grip, and a little latch detail. And we're going to take it through the usual plastic design checks that we should do before releasing for tooling. Okay, so first up, wall section. So we're basically looking for any very thin wall section areas that might have trouble filling, or very thick wall sections that may cause some sort of sinking in the moulding. So in SOLIDWORKS we can use a feature called thickness analysis. It's pretty self-explanatory. First of all, we'll look at thin areas. The common wall section, or the standard wall section of this part, although it's a variable part as far as wall section goes, is about 2 millimeters. So we'll do a quick calculation and it'll come back and show us using color gradients where the thin sections are in this part. If you end up with thin wall sections, you can have trouble actually filling them, and then you have to put too much pressure into the plastic to fill those parts, which can also be an issue, can cause parts to get caught in the tool, hard to eject. So here we go. So obviously this spring section has to be thin, and it comes down to about 0.8. 0.8 is really sort of the limit that I like to go to for most parts. Anything below 0.8 and you start having trouble filling it. You can see is 1.9 around this area here. The finger grip here is 1 mil, 1.2. Thin area here is, it's actually just a little bit under 0.8. I'm not terribly worried about that because there's so much thick area leading into these very short thin areas. It's not difficult to fill those. When you have a long thin area, the longer it gets, the harder it is because the plastic chills off and won't necessarily get to the end of that detail before not being able to be pushed through any further. So we'll also now look for some thick sections. And the main problem with thick sections is it causes sink marks. It's also a waste of material quite often too, if you have big build-ups, and also inconsistent cooling. The thicker the area, the slower the cooling. While it's still cooling, it's shrinking. That's why we get sink marks in thick areas, because that is actually shrinking for longer than the rest of the part. So you get inconsistent shrinkage. Right, so as expected, these diameters are the thickest areas, getting up to around 3 mil diameter actually, I think they are. We could core this part out, run a diameter up into it, which with plenty of draft so I won't get stuck. In reality, I've done a few of these parts with this sort of detail and it hasn't been a problem. It's just this bit here is just over 2 mil, a little bit thickening around here where I've blended the spring into the body. One of the things I did do with this part was I did core out this whole finger area so that it wouldn't get too thick. Originally it didn't have this detail here and this radius. So I'm happy with that. It's a very small part anyway, so there's not a lot of availability to core it out, other than maybe these pins if we're really strict about it. Okay, the next section is looking for sink marks. Well, we've just discussed sink marks and sink mark prevention. So this really comes down to wool section thickening prevention. So we're going to now look at draft. Is there adequate draft? And part of that is the draft going in the right direction? So in SOLIDWORKS has this draft analysis tool. Your CAD of preference hopefully has this sort of thing too. I think the minimum draft we have on this part is 1 degree draft. So the red detail shows the detail is moulded by the tool on the top. The green is what's moulded on the tool on the bottom. Yellow, as we can see, is 0 angle draft, or less than the 1 degree that I gibber. So there's no draft on this detail yet. And there's also no draft on this here too. But also, underneath this little detail here, there's no draft there, or it's less than 1 mil draft, 1 degree, I should say. And then this red, because that's being pulled from underneath, is actually in the wrong direction. So that would actually cause an undercut. So that needs to be fixed. So that's a bit of a fail. Next up, we look for undercuts. Now, obviously we've found the undercuts. Just to show you what happens when we do the undercut. We just select a face that's parallel of the line of draw, which this face is here. And you can see these red details, these are undercuts. So they need to be fixed. Otherwise, it would basically get stuck in the tool. That's what that's saying. It's getting stuck in the tool. So that's a fail. A defined part line. So you can see this part here has got this defined part line. That's all sort of nice and horizontal through here. Then to create this spring finger, then there's an angled part line and then another horizontal to get a nice part at the right point of this radius so that we don't end up with an undercut there either. Then the part line travels up here. From here, it travels along the bottom there, so that's the part line also. So it does have a good part line. It's defined, but the draft angles aren't in the right direction, or there's undercuts. So it needs to be fixed. The next thing, shutoffs. So shutoffs is where, and this actually has a big shutoff. To create this part here, so it's not an undercut, we are actually coring a big bit of steel up from the bottom of the tool. So with this green section, it's pulling from underneath, when the tool comes apart, it's actually moulding the underneath of this. To do that successfully, we need to be able to have this part of the tool shut off against the red part. And to do that, we need at least 3 degrees, which you can see we've got 3 degrees there. 3 degrees there. 3 degrees in here as well. If I actually change the draft analysis to 3, looks like that face. 3 degrees, and you can see that those shutoffs are 3 degrees. There. We'll put this back to 1. This back face, because it's not actually shutting off against it still can be 1 degree. So that's fine. Okay. Corner radii. Are there adequate corner radii? And the one after that is stress points. Are there stress points? So it's really part of the same thing. As you can see, this little flexible finger here, we'll turn off the draft here. Flexible finger is going to be flexed in this direction, so this will be a stress point if that didn't have that radius there. We should probably put radiuses around the whole thing just to get away these little sharp notch areas that can cause fractures. The other area that's going to be stress on this part is between these diameters when it's pivoting on and this latch. If you pull on there's actually a door that this attaches to. If you pull on the door, it's putting pressure between the diameter and the latch. This latch under here's got a sharp corner that could fracture through there. These could fracture around there too, so they're prime candidates for radiuses being required. Then these areas in here, radiuses, we want to break all these edges because the more we can put radiuses in, the less stress you mould into the part as it does a sudden change of direction around a sharp corner. The more we can blend with radiuses, the less stress in the part. And we get a better and quicker flow of plastic when we're filling the tool. There's no side cores in this, it's all an open shut tool, so we don't have to worry about side coring and side core entrapment. And the other one is screw bosses. And there are no screw bosses on this. So the two main things this fails on is draft and undercuts, and also there are some radiuses that need to be added. So I'll come back to you with what I would recommend. That's what would go out in the report if you were asking us to do the design check. If you ask us to resolve this, I will come back and show you in part 2 of this the resolution to these issues and what the part would look like after that. So stay tuned. Okay, I'm back with the part. We've made a few changes to it to resolve some of these issues. But the first issue was the draft. There's some undercuts because the draft was going the wrong direction, and also there was no draft in some spots too. So we'll do the draft analysis again and I'll show you what I've done. Okay, so as we can see now, there's draft on this side here. A little bit complex. This is just a straight draft pulling down the same as the rest. This one here is a little bit of a more detailed angle, changes in angles and things to get it all working nicely because of the complex split. As you can see, that the split line is very well defined. It's all green on top, red on the bottom. Underneath, we don't have those back to front draft, reverse draft that were causing undercuts, and there's draft on the end as well. So it's all red and green, which means it's all got draft and it's pulling one side or the other, and still we have this shut off created to do this detail here. So that's looking really good, and as a result there are no undercuts in the part, so that will come out of the tool nicely. The next thing was radiuses. We've now got some nice radiuses around this spring finger, or this leaf spring, and also we have radiuses around this diameter. We'll just turn off, there we go, radiuses around the diameter, so when someone pulls on the door this is attached to, it's less likely to fracture the diameters off, or also there's a diameter under a radius under there that will stop that from fracturing also. So only very small radiuses, there's actually only 0.2 of a mil, but by breaking those sharp corners you're taking away a very sharp detail that a fracture or a crack can migrate from. Makes it a whole lot tougher. Underneath we've got some nice radiuses just to really make it better for moulding. You'll see, because of what's happening with shut off here, we don't want radiuses running up here, so you can see this radius is blended out to 0 there, but it's nice radius running around there. So that part's now ready to be released for tooling, and all those issues are resolved. That's what we do here, and if you need help with this sort of thing, get in touch, reach out, and we can help you, certainly. If you found this video useful, could you please give us a thumbs up and subscribe. If you would like to get some more information about this subject, we have a free downloadable PDF of our Release for Tooling Readiness checklist. This checklist is what we use here at SCAD Design to ensure that every part we release for tooling is injection moulding ready. Just click the link in the video or go to scaddesign.com.au/wedesignplastics. If you'd like some help in this area or would like a second set of eyes, we offer a tooling readiness checking service. You send us your 3D file and we send you a report with a simple traffic light system so you can see if your design is good to go or needs some work. We also offer a service that will make the necessary changes to a part design to make it tooling ready. And lastly, we of course can design your injection moulded parts from scratch to meet your needs. Remember, keep it simple. Thanks for watching and bye for now.